Hi, welcome back. In this lecture, you learn how to use mathematical relations to store information of the abstract machines. You will also learn operations on these relations that can be used to manipulate this stored information. Let's go. First, let us talk about Cartesian products. Let us suppose we have a set S and a set T. The Cartesian product of S and T, which is represented with S star T, is a set composed of all pairs X and Y, where X comes from the set S and Y comes from the set T. For example, if S is equal to the set 0 and 1, and T is the set 2 and 3, we have that the Cartesian product of S and T is a set composed of the pairs 0 and 2, 0 and 3, 1 and 2, 1 and 3. Now, let us consider an example of a relation. Let us suppose we have a set of photographers and a set of cameras. The set of photographers is the set photographer, which is equal to the set composed with the following icons: Anna, Bob, Chris, Dave, Elizabeth, and Francis. And the set of cameras is represented with the set camera, which is equal to the set Canon, Kodak, Hasselblad, Olympus, Pentax, and Minolta. A relation between these two sets, then, could represent ownership. For example, if the pair Anna and Canon is in the relationship, this could mean that Anna owns a Canon camera. We could have many of those pairs. For example, the relation owns could be graphically represented as follows. We have the set of photographers on the left-hand side and the set of cameras on the right-hand side. And we could say, like, Anna owns Canon and Bob owns also a Canon camera. Bob owns Kodak, Chris owns a Kodak, Chris owns a Hasselblad, Chris owns a Pentax, Dave owns a Pentax, Elizabeth owns a Minolta, and Elizabeth also owns a Pentax. This graphical representation, if you write in a textual manner, would be represented as follows. We have the relationship owns equals the set composed of the following pairs: Anna Canon, Bob Canon, Bob Kodak, Chris Hasselblad, Chris Kodak, Chris Pentax, Dave Pentax, Elizabeth Pentax, and Elizabeth Minolta. Or, using the maplet notation, this could be transformed into the following set. Notice that a relation between two sets S and T is a subset of the Cartesian product S star T. Therefore, the type that represents all possible relations between these two sets is defined as the power set of this Cartesian product. So, S relation T equals the power set of S Cartesian product T. A relation R, therefore, between these two sets is a member of this set. So, a relation R is a member of the relation between S and T, where S is the source set and T is the target set. If we go back to our example, we have the set photographer and the set camera. And the Cartesian product of photographer with camera is the set of the pairs Anna Canon, Anna Kodak, and so on. All possible subsets of this Cartesian product is the power set of the Cartesian product between photographer and camera, which equals the set that contains the empty set, the set containing only the pair Anna Canon, the set containing the pairs Anna Canon and Anna Kodak, and so on. So, the relation owns that we have just shown belongs to this power set. We can use the relation owns and operations on relations to answer the following questions. Does Bob have a camera? How many cameras does Elizabeth own? Which cameras are owned by Chris and Dave? Let us now learn about operations that will allow us to answer these questions. The operations on relations available on the B method are domain, range, domain restriction, domain anti-restriction, range restriction, range anti-restriction, relational image, relational inverse, relational composition, and relational overriding. Let us now talk about each of these operations individually. The domain of a relation R between sets S and T is a set containing all elements of S that are related via the relation R with some element of T. Therefore, the DOM of R is the set of all x's, where x comes from the set S, and there exists y, where y comes from T, and x is related to y in R. In our example, the domain of ons is a set containing Anna, Bobby, Chris, David, and Elizabeth, because all of these elements are related to some element in the camera set. On the other hand, the range of a relation R between sets S and T is a set containing all elements of T that are related via the relation R with some element of S. Therefore, the range of R is the set containing all y's, where y comes from T, and there exists x, where x comes from S, and the maplet x to y belongs to the relation R. In our example, the range of ons is a set containing Canon, Kodak, Hasselblad, Minolta, and Pentax, because these cameras are related to some photographer. The domain restriction on a given set U of the relation R between sets S and T is a set containing all elements of R whose first element of the pair belongs to U. So, the domain restriction of R on the set U is a set containing all pairs X and Y, where X and Y belongs to R and X belongs to U. In our example, we have that if we have a domain restriction on the set Chris containing Chris only of the relation ons, we have the relation Chris Kodak, Chris Hasselblad, Chris Pentax, basically because the first element of these pairs is Chris. On the other hand, the domain anti-restriction on U of the relation R between sets S and T is a set containing all elements of R whose first element of the pair does not belong to U. So, the domain anti-restriction of R on the set U is a set containing all pairs X and Y, where the pair X and Y belongs to R and X does not belong to U. In our example, we have that if we have the domain anti-restriction of the relation ons on the set Chris, we have the relations containing the pairs Anna Canon, Bobby Canon, Bobby Kodak, Dave Pentax, Elizabeth Minolta, and Elizabeth Pentax. Those are the pairs of the original relation ons, removing the pairs where Chris is the first element. We have the same sort of operations, but now focusing on the range. The range restriction on U of a relation R between sets S and T is the set containing all elements of R whose second element of the pair belongs to U. So, the range restriction of R on the set U is the set containing all pairs X and Y, where X and Y belongs to R and Y belongs to U. In our example, if we make it the range restriction of ons on the set containing only Kodak, we have the relation Bob and Kodak, Chris and Kodak, basically because those are the pairs from the original relation ons whose second element is Kodak. On the other hand, the range anti-restriction on U of the relation R between sets S and T is the set containing all elements of R whose second element of the pair does not belong to U. So the range anti-restriction on U of the relation R is the set containing all pairs X and Y, where X and Y belongs to R and Y does not belong to U. In our example, if we make the range anti-restriction of the relation ons on the set containing Kodak and Canon, we have the relation containing the pairs Chris Hasselblad, Chris Pentax, Dave Pentax, Elizabeth Minota, and Elizabeth Pentax. Basically, because those are the pairs of the original relation ons, whose second element is not Kodak or Canon. We now define the relational image of a relation R between sets S and T on a set U, which must be a subset of S. This relational image is a set containing all elements of T that are related via the relation R with some element of U. So the relational image of R on the set U is the set containing all Y's, where X and Y belongs to R and X belongs to U. In our example, the relational image of the relation ons on the set containing Chris and Elizabeth is the set containing Kodak, Hasselblad, Minota, and Pentax. Now we talk about the relational inverse. The relational inverse of a relation R between sets S and T is the set containing all pairs Y and X, such that X and Y belongs to the original relation R. So the relational inverse of a relation R contains all pairs Y and X such that X and Y belongs to R. In our example, we simply have that the relational inverse of the relation ons is the relation containing the pairs Canon Anna, Canon Bob, Kodak Bob, Kodak Chris, Hasselblad Chris, Minota Elizabeth, Pentax Chris, Pentax Dave, Pentax Elizabeth. We have just changed the position of the elements of the pairs. The next operation is the relational composition. This operation composes two relations. For example, if we have a relation R0 between sets S and T, and the relation R1 between sets T and U, the relational composition of R0 and R1 is a set containing all pairs X and Z, such that X and Y belongs to R0 and Y and Z belongs to R1. So the relational composition between two relations R0 and R1, in which the target set of the R0 equals the source set of R1, is the set containing all pairs X and Z, such that X belongs to S, Z belongs to U, and there exists a Y such that Y belongs to T, and the pair X and Y belongs to R0, and finally the pair Y and Z belongs to R1. In our example, if we consider a relation called takes, that says that which camera takes which equipment, and let's suppose it equals the relation Canon 35mm, Kodak disc, Hasselblad 120 roll, Minota 35mm, Olympus 35mm, and Pentax APS. And then we compose the original relation ons with the relation takes. We have, for example, in the relation ons that Anna is related to Canon, and therefore the composition gives us the pair Anna 35mm. And we make this to the whole relation ons. As a result, we have that the relational composition of on and takes has elements of the photographer set and elements of the equipment set. So we have the relation Anna 35mm, Bob disc, Bob 35mm, Chris disc, Chris 120 roll, Chris APS, Dave APS, Elizabeth 35mm, and Elizabeth APS. Finally, we have the relation overriding. The relation overriding takes two relations, for example, R0 and R1, between two sets S and T. If we have the relation overriding of R1 over R0, we have the set containing all pairs X and Y of R0 such that X does not belong to the domain of R1, and all pairs X and Y of R1 such that X belongs to the domain of R1. So the relational overriding of R1 over R0 equals the domain anti-restriction of R0 on the domain of R1 union R1. In our example, if we have the relational overriding of the pair Chris Olympus on the original relation ons, we have now that Chris is related only to Olympus. We are now able to go back to the questions we have made at the beginning of the lecture. The first one was, does Bob have a camera? That's the same as ask if the card of the relational image of the relation ons on the set containing only Bob is greater than 0, while the relational image of the relation ons on the set containing only Bob is the set containing Canon and Kodak, and the cardinality of that set is 2, which is trivially greater than 0. So the answer to the question is yes, Bob has a camera. The second question was, how many cameras Elizabeth owns? That's the same as ask the cardinality of the relational image of the relation ons on the set containing only Elizabeth. That's the same as asking the cardinality of the setting containing Minota and Pentax, which is the relational image of the relation ons on the set containing only Elizabeth. And the cardinality of that set is 2. So Elizabeth owns 2 cameras. The final question was, which cameras are owned by Chris and Dave? That's the same as asking the relational image of ons on the setting containing only Chris and Dave. And that is the set containing the cameras Kodak, Hasselblad, and Pentax. So Chris and Dave own the cameras Kodak, Hasselblad, and Pentax. And that completes all the operations we have on the B method for relations. We are now able to present an example of a machine called Access that stores information about printers, and it stores the options that each printer has. The users are able to add and remove options from these printers, and it's able to ask if a given printer has a given option. We're going to present this example in both Pro B and Atelier B. Let's go. The machine Access has 3 sets. A deferred set called Printer, which represents the printers of the machine. A deferred set called Option, which represents the options that printers may have. And a set called Permission, that contains 2 members, OK and No. This machine has a variable called Options. In the invariant, we declare options as a relation between printer and option. We initialize this variable with the empty set. So initially, the printers have no options. We have now 3 operations. 1, to add a given option to a given printer. 1, to remove a given option from a given printer. And 1, to query if a given printer has a given option. The first one, add, receives a printer PP and an option OO, and includes in the relation options the pair PP-OO. The second one, remove, receives a printer PP, an option OO, and removes from the relation options the pair PPOO. Finally, the operation option query receives a printer PP, an option OO, and gives an answer OK if the printer has that option, and an answer no if that printer has not that option. So, if the pair PPOO belongs to options, the answer becomes OK. Otherwise, the answer becomes no. We may now initialize this machine, and we have now options for adding, removing, and querying about the options of the printers. Initially, here we can see that options is empty. Let us now add options 1, 2, and 3 to printer 1, and the option 6 also. So now we have the option 1 to printer 1, option 2 to printer 1, option 3 to printer 1, and option 6 to printer 1. We can remove, for example, the option 6 from printer 1, and that element is removed from the relation options. Finally, we can also query if, for example, the printer 1 has option 4, which we know it doesn't. So the answer is no. Or if the printer 1 has option 1, which we know it has, so the answer is OK. And you can actually make a random animation of 100 random operations, and as we can see, the invariant has been respected in all these operations we have done. So that gives us an idea that the machine is behaving according to the requirements of that machine. So let us now move to Atelier B to verify if the machine is consistent. We have now created a project with called Access, with the Access machine in it, and we have the same specification that we presented using ProB. And we can see here that all the proof obligations generated have been automatically discharged by Atelier B, proving that our machine is indeed consistent. That finishes our example of the Access machine in both ProB and Atelier B. And that's all for today's lecture, which I hope you enjoyed. See you in the next one. Bye.